So we're still dealing with size, but now we're going to deal with ionic atoms. So ions, these are your cations or your anions, and we're going to do an example of each. We're going to start with the cation, and then we're going to look at the anion. So here's what we have for our aluminum. If you need to double check on the chart, you can. Aluminum has 2 electrons in the first energy level. That's the first energy level. So in one, it's 1s2. It's 2s2, 2p6. So there's a total of 8 blues in this section. And that's the second energy level. And then the third energy level, it's 3s2 and 3p1. That's what you get if you go over the periodic chart and you figure out aluminum, you'll get that configuration. And on these energy levels, notice that they are combining the S's and the P's together. If we take out our valence electrons, we'll have a noble gas core, which is very stable. We'll have 8 here, which is very stable. It will end up looking like this. We'll have those core electrons. And then we'll have 1, 2, 3, 4, 5, 6, 7, 8. And we won't even have the outer electrons at all. So if you look at this, you can tell just by looking at it that the atom on the right is going to be smaller because he doesn't have any valence electrons at all. So what if we were talking like an atom that was maybe one more over somehow and that we still had one valence electron? Even if we have one valence electron, remember we've got that nuclear pool going on. So we're going to be looking at what happens when we have that one valence electron after we look at what happens with the sulfur. Just note that I have 13 protons that are pulling on now what are 10 electrons. So I'm going to write that off to the side so don't forget it. 13 protons that are pulling on 10 electrons. And remember, even if they're shielded, what happens because of effective nuclear charge, right? You're going to hopefully see what's going on. All right, so then we're going to look at sulfur. And in this case, sulfur, he likes to gain electrons, right? So we're going to go ahead and put all of his electrons on here. His configuration, by the way, is 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 4. So if we can tell on this section, we're only 2 electrons away from being a full octet. So we're at 6 and we just need 2 to be a full in that energy level. So we're going to go ahead and compare him. There's our core electrons. Then we've got 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to go through and put on my valence. I already had 1, 2, 3, 4, 5, 6. And I'll just change the color slightly so that you can see here's our other 2 valence electrons. So now what we have are 16 protons pulling on 18 electrons. So hopefully what you can see is that this nucleus has a lot more pull on those electrons. Even taking out consideration for these, which are the core, we still have 10 protons pulling on 8 electrons. Over here, now our protons have less pull because we've got extra electrons in there. So you can imagine that actually these electrons are floating further and further from the nucleus as compared to their counterpart over here. They also have repulsions amongst themselves that they're dealing with, which are also pushing them farther out. So the overall idea that you want to get out of this is that when atoms form cations, they will become smaller. They have less electrons. They're going to have a greater pull on the positive charge on the remaining electrons. In contrast, when you have extra electrons, there's not as much nuclear pull left for them. And so the anions are always going to be getting larger than their neutral equivalent, and the cations will always be getting smaller. So let's look at how this works with this chart that we were just talking about, where you go in that corner direction. So let's look at the fluorine when they're neutral, fluorine, neon, and sodium. So right up here, fluorine, neon, sodium. So fluorine, neon, sodium. Neutrally, fluorine is one of the smallest atoms out there. We also have neon, which is also extremely small. And so if you're going with this directional idea, then you can go ahead and include neon in there. And then sodium, look how much larger sodium is. So you would expect this to be the trend, that fluorine is smaller than neon, which is smaller than sodium. In the very least, fluorine and neon could be similarly sized. So this is what you expect, this pattern right here. Isoelectric, we're going to compare some isoelectric electrons. That means that they have the same number of electrons. So before we were just comparing neutral to charged. Now we're going to compare charged elements that have the same number of electrons and see how that affects this trend. So if we started with sodium, and this is sodium, this is 11 protons and 11 electrons. If we start with him and we make it sodium plus, that's like taking off this electron, which means that we have 11 protons pulling on 10 electrons. And if you remember, what that means is that these guys are getting pulled in more tightly, which makes him quite small, which is in sync with the idea of a, an atom that's positive getting smaller. And then we have neon, and we're not changing neon. He has 10 protons that are pulling on 10 electrons. So that one's nice and even. And then over here, we have fluorine becoming fluorine minus. So what we're doing is we're adding in an electron, like right here. Before, he had 9 protons pulling on 9 electrons, but we just added one, so that's 10 electrons. Notice 10, 10, 10. But now our protons don't have as strong of a pull. And so now these electrons on the outside can start moving further out. They have extra repulsions because they've got an extra guy in there amongst each other also. And this is going to be a larger atom. So if you are comparing isoelectric, make sure they're isoelectric. If you're comparing like something in a different like row that's further down, those are always going to be larger, like further down on the chart. Anything that's further down is going to be larger. Just make sure what you're comparing is isoelectric. And within isoelectric, the general good rule of thumb is that the more positive is smaller, and then you get to your neutral one, and then the more negative is larger. There'll be some practice problems on this on the homework too. I should put that over here. Maybe like that. So the trend for them when they are charged is that Na plus is smaller than neon, which is smaller than F minus. Crazy times.